Hello, this is Dr. Asan Abdullah with the course Deep Reinforcement Learning. And the topic which we are covering is basic gradient descent, which is third topic in the list of topics. And this third topic is divided into three subtopics. That is lecture 3A, 3B, and 3C. Is that the difficulty progressively increases of the topics, of the contents of the topics. That is why 3A, 3B, and 3C. So we move towards the lecture itself, which is developed using the personalized learning management system, easymcq.com/goget. Personalized learning management system is accessible using the URL which is given in green color on the screen. Now, how to make use of this learning management system, that is shown in 6 videos, which are given in a URL in blue color on the screen. So there are many wonderful features in this personalized learning management system which are not there in some of the more popular learning management systems, major learning management systems. So this is all possible because of the feedback which has been given by users like you and incorporated into this personal learning management system. So one of the biggest features and useful features is full text in the content available in the learning management system. So you can type in keywords, short, long, advanced, ensuring the order and so on, and get all the contents which is relevant, which is color coded and it's available to you. And then of course, some people may have visual disabilities. So that is not catered in many advanced and major learning management system. So in this easymcq.com, the students or the users have the facility and the ability to change the font type, the font color, the line spacing, and so on to make it more readable, to make it more interactive and more useful, right? And of course, you can also track your progress. For example, which topics you have covered, which subtopics you have covered, and so on. That is there. And of course, you can evaluate your learning and knowledge accumulation through online exams. You can do multiple of exams, and their aggregate scores are recorded and stored. You can access them, and it also identifies the weaknesses. And of course, the data and the content is presented in a hierarchy which saves the space and so on. So I would urge you to look at those videos. So there are two basically learning approaches. One is the traditional learning approach, which is slides based and which has its own limitations. And then is the Q&A, question and answer based learning approach, which is proactive, which is engaging, which is very adaptable, and which is very thought provoking also. And of course, the traditional approach has a lot of details. So the approach which has been followed is a blended approach or blended learning, that is making the best use of the both approaches. So we have the list of topics in front of us, and we are at the third topic, which is the basic gradient descent, which consists of 15 questions and answers. And these Q and A's are basically concepts which are further divided into the three lectures or subtopics 3A, 3B, and 3C. So here we have those subtopics or the question and answers in detail. So the yellow is 3A, which is this lecture. And as we move, then we move on to 3B and 3C. Further ado, we move on towards those concepts and discuss them in details. So we are at the video lecture 3A, Deep Reinforcement Learning. And the topic which we are covering is gradient optimization. So this basically this first concept, what is gradient descent and why it is used in deep learning, that is very important, that is very critical. And if you understand this and the next one, so you will be able to understand many aspects of this course and neural networks also. So it's a good thing that there are a lot of description available. The video is here, the diagram is here. So let's start. So what is gradient descent and why it is used in deep learning? Well, gradient descent is also used in neural networks, and as you know that for deep learning we have many more layers of neurons. So gradient descent basically it's a fundamental optimization algorithm. Okay, and the objective is something which is called as the to minimize the loss function. So what is the loss function? The loss function is there's a difference between the predicted output and the actual label. So we are looking at annotated data, right? So for example, we have images of say dogs and cats, and how what is the difference between, or how different, or there's a mismatch or a match between the predicted output and the actual label. So that is the loss function, right? So the objective of gradient descent is to minimize the loss function. So obviously, when the loss function is minimized, the accuracy increases. So what is the gradient part? So this is basically the derivative rate of change of the loss function, okay, with reference to the parameters of the model, okay. So what are those parameters? The parameters are the weights. The weights. I'll show you the diagram in the next Q&A, and then we have a whole topic of neural nets, so this will become clear. So weights are the connectivity, the edge weights between the neurons, and the biases. We'll talk about it. So basically, what do that gradient does is the direction in which the loss function increases most steeply, right? So the objective is to decrease the loss function, right? So we are descending, right? So it means that there is a minima in the loss and the weight space, and we would like to reach that minima. And of course, we start with a very simplistic approach of a single minima, but in real life there can be multiple minima also. So let's look at the concept of the gradient, the gradient concept. So what does the gradient means? Okay, that is the direction, all right, and with the steepest increase of a function. Okay, so in deep learning, it like kind of identifies how the model's parameters are affecting the loss. So that's what it's identifying. So when we compute the gradient of the loss function, okay, with respect to the weights, I'll show you. So we understand that how to adjust the weights to reduce the error. So let me first give you an analogy, okay, and then I'll show you this diagram and look at the further stuff. So this is very interesting. So consider that there is a this is basically this is the cost of the derivative. So we have cost at the y-axis and the weight of the edges in the neurons, which is the x-axis. So consider this a blind person, and that blind person has to uh, go down into travel over a valley or a mountain, okay? And the objective is to reach this minimum cost. Now this person cannot see, but the person can, of course, can feel and understand that the person is ascending or descending, right? So this blind person is like our this is going to go for the objective function. So this is the gradient, and this is the initial weight. Initial weight is the starting point, and corresponding to that starting point there are weights assigned to the neurons. That's in the next picture. So this blind person gets down taking steps, right? These are steps, incremental steps. So you can understand then if the steps are small, it is kind of it'll take more time, and it is more accurate also. But if the steps are big, it will take less time because one step can be here, the other could be here, so there's an increase. So come back down. So the objective is to reach this point, the minimum cost. So at this minimum cost, we have these weights such that the error function is reduced. Okay. So this is so our like now this is an oversimplistic approach because in real life that's not the case. There can be multiple minima, and we have a multi-dimensional space also. But you get the picture. So this is what we are trying to achieve. All right. So let's go back to the bullets. So now I believe it should be easier to understand. So now you know what is meant by the concept of the gradient, and then is the descent direction. All right. So the gradient descent basically updates the parameters of the model. Okay. Uh, in the opposite direction of the gradient, that is moving towards the lower loss, which I've just shown you. So what does this descent ensures? Why it is called descent? Because if you are at the right side of that curve or towards the left side of the curve, the objective is to go to the minima. So it's always the descent. So descent over the gradient. So that's why it's called gradient descent. So it ensures that at each step, the model ideally becomes more accurate. But of course, if the steps are long, it can kind of overstep that thing. So of course, when so we are following a negative gradient, all right, and of course, what it does, it guides the model towards the optimal performance during training. We are assuming that there is only a single optima, but there can be there can be local optima, and of course there is a single global optima. So that is a more complex thing. But we are right now we are restricting ourselves to simple situation. So then what is loss minimization with reference to the picture you just saw? So the objective of or the primary goal of the training is the training of those the weights associated with the neural net. So once those weights are properly done, properly adjusted, then of course when unlabeled image is shown, okay, then there is more likelihood that it gets properly labeled. So maybe that could be binary also. So this is a cat, this is a dog versus, right? So what is done in loss minimization? Gradient descent. Now you know what is gradient. Now you know what is meant by descent. It kind of iteratively, okay, it goes over and over again and iteratively reduces the loss, right? And how that is reduced by adjusting the model weights. In the next Q&A, I will show you those model weights also. So what happens that ideally at after each step, right, the predictions are close to the ground truth. That is ideally, and of course that improves the model's accuracy, okay, and over time it improves the generalization also. What is generalization? We have already discussed in machine learning. So what actually happens in model training? What happens in model training is that basically gradient descent is the core algorithm, okay, for training the neural networks. And iteratively and repeatedly the weights are updated, and how those weights are updated based upon the gradient loss, okay, until we are satisfied with the performance that we say, oh, this is defined with accuracy. And of course without gradient descent there would not be no systematic way, right, to optimize any models, any deep learning models with millions of parameters. All right. So now we move towards some rather more technical stuff. Okay. So I close this. All right. I close this and we move on to the more. So how gradient descent in deep learning is linked with annotated, say, it could be images, it could be audio, it could be text also. So how it is linked with? Basically, so there are quite a few bullets here. So what happens in let's consider deep learning and annotated images, right? So we have a image and a label pair, right? So every image has a class, and of course we would like to have, say, maybe bounding boxes on the image, or we would like to have segmentation masks, okay? And maybe those are already placed, right, for uh, training the supervised model. Okay, deep learning is supervised learning. So gradient descent, of course, plays a central role in this training process, right? And what is the central role that we've discussed? By minimizing the difference between the model's predictions and the ground truth annotations. Okay. So what I'll do is first I'll show you a diagram and then we will discuss that diagram. Okay. So let's take it. So this you need to understand and all understand all of this. So all right. Now this should be very clear. So we have these inputs. So inputs are the x as shown by x, and the output is the class label y. Right? So this is the actual class label y, and this is the predicted class label y hat. This is the output, this is the input class label. So we are assuming a system which predicts the class label as 0 or 1. So you train the system using images of cats and dogs, and you ask that this image is a cat or a dog, and it tells you 0 and 1. All right. So then there is these are the inputs, and these are the weights. So weights are the how much significance you give to certain input. Okay, okay. So then we have something which is called as the transformation function. So these are the weights and transformation function. So basically, what will it will do is that it's a linear operation. So what will it do? The details are given before. So it takes the input, okay, and maps to a new space using the learnable parameters. These are the learnable parameters, and usually it is defined as z is equal to wx plus bz. So w are the weights and b are the biases. Weights and the biases. So where do they come from? They come from the error. Okay, they come from the error. All right. So then there is something called as there is something a loss function which we have discussed, and then is the activation function. So what is this activation function? That adds non-linearity to the neural network, because the world which we are living that's not linear. So with that non-linearity, okay, the neural network is able to learn complex patterns from the annotated images, right? Then is the activation. So we have this transformation, we have this activation function, and then we get the predicted output. Now that predicted output is compared with the class label, actual class label, and whatever that error is, that error basically is used to adjust these weights, and this is called as the back propagation. Okay, and these weights are updated. So what we have, so we have this predicted output and we have this updated, how that this gets updated based upon this, and this is how it works, right? So it's if you look at it, it's fairly straightforward. It's not complex. And what happens in deep learning is that these layers, this is one, so these increase, and then of course there's the interconnectivity also. So we have, and that we have discussed in the first topic. All right. So let's go into slightly more detail. Why I'm saying slightly more details, because the details are given here. So we look at the bullets, right? So I have explained to you. I will go over the bullets, okay? And then of course you need to do the reading. So this is a supervised learning, right? Supervised training process. So we have those annotated images. It could be text also. It could be audio also, okay? And that, so that is the input output pair, right? And that is used by the model to learn the correct mappings during the training. And what is that what is that learning? That learning is adjustment of the weights. So the model uses the labels, right, and the predicted values, and computes the prediction errors. And then what gradient descent does is that iteratively, okay, minimizes these errors, right, and by adjusting what the model parameters. So that results into supervised learning, which is structured, which is efficient, and which is optimized. The blind man approach. Okay. So finding the way without actually seeing it, feeling it, and then adjusting yourself. All right. So then is the transformation function that we have discussed. Then we have the loss function that we've also discussed. Okay, the activation function. So the activation function introduces non-linearity. So I'm talking about this activation. So that introduces non-linearity into the neural network. So it can learn complex patterns from those annotated images. So what it will do is they transform each neuron's output, okay, before it is passed to the next layer. So there are common functions for that activation, that like sigmoid, okay, which ensures that the gradient descent can model detailed, intricate visual relationships in the data. And then is the back propagation mechanism. So we have a whole topic in this course on back propagation. So what is back propagation? It computes how each parameter contributes to the loss. Each parameter, okay? And how it is done by propagating the errors backward through the network. And then, of course, we also have, which you have seen, that we have the annotated labels also, which define the loss. And based upon this loss, the gradient calculations are done. And these gradient calculations, blind man approach, guide how the weight should be updated. So the blind man sees that uh, uh, that he or she is not going down. He actually is a blind man, so takes an alternate route, okay, or steps back or whatever. So what the purpose is to improve the future predictions. Okay, then are the updates of the weight updates, which is already seen in this diagram. So weights are updated to minimize the loss, right? So and the annotated images ensure that these updates are meaningful. These updates are correct, right? So what happens is that the correct labeling increases, and when these updates are done repeatedly, of course that improves the prediction accuracy, and which is basically the core of supervised deep learning, right? And then of course is the model generalization. So model generalization basically, so it gradient optimization, okay, this helps to it helps the model to learn features by applying them to the unseen data. So when there is generalization, there is not working based upon memorization. Okay, because then it's unable to capture the underlying patterns. So what is the objective? Objective is to improve the training performance and the real world applicability. So I would suggest that you spend some time and read this stuff, this material, and match it with this diagram. This is a wonderful diagram and it explains a lot. Okay, and it is easy to understand also. And if you're interested, there's a lot of stuff to read. All right. So let's go into some more detail. How do gradients help minimize the loss function? How do gradients minimize the loss function? Just slightly more detail, just to kind of reinforce the concept. And I'll show you. First, let's take a look at a diagram also. All right. So still we have a single minima. We still have a single minima, but they can be multiple also. So as before, we have the loss function and the weight parameters. So we are looking at the gradient. Okay. So basically the rate of change. So this is basically we would like to reduce. So this is this is more steep, this is less steep, and so on. So we are trying to, and alpha is the learning, alpha is the loss, change of loss with respect to the weight, learnable parameter, which is the weight, right? All right. So and this is the gradient, the rate of change, right? And we are moving in the opposite direction. So we are trying to uh, so this is the way we are working. All right. So let me explain this to you. So keep in mind this alpha also, which is the learning rate. So if we increase or decrease the learning rate, we have the corresponding result also, right? This determines the step size also. So I'll basically show you a diagram also with reference to the step size also. So there is certain amount of repetition here about gradient. We know what gradient is, and we also know the what is loss function, right? So okay, now let's look at this parameter updates, because the remaining we have already covered. Parameter. So what happens in parameter updates? So while the training is done, gradients are used to update the model parameter, which is the weight. And how it is done, I've shown you by subtracting a fraction of the gradient, okay, which is scaled by the learning rate, which was alpha. So what it does, this process of subtracting and using the fraction, this kind of nudges or slightly moves the model towards the global minima to reduce the loss. So what happens is that the predictions are gradually improved, right? And the performance also improved with each update that I've shown you. So W dash is equal to W minus alpha into the rate of change of L with reference to W. Okay, so training iterations. What is training iterations? So there are multiple iterations that we have seen in the previous Q&A also, and the parameters are updated repeatedly. So what happens over time? Now these small adjustments, depending upon the value of alpha, they kind of accumulate, and as the saying goes, the slow and steady wins the race. So they steadily decrease the loss function, and by virtue of this iterative optimization, okay, so that enables the model to learn from data and generalize well to the unseen inputs. Okay, so that was just kind of addition to what was covered before. Now this is now here's some more. Now now there are different types of gradient descent. Okay, this is called as the batch descent and the stochastic and mini batch, and then there are other things which need to be discussed. Okay, so so let me let's first look at the bullets. The diagram is here, right? The diagram is here. So the diagram is it's better first we look at the bullets and then come to the diagram. So let's take a look at the bullets first. So we have different we have types. It's kind of standardized three types, okay, which is batch, stochastic, and a mini batch. Okay, so basically the difference between them is how much data is used and how it is used to compute the gradient at each training step. So what is batch gradient descent? Batch gradient descent. So batch gradient descent uses the entire data set to compute the gradients, all the data. And those model parameters are updated once per iteration. So of course, this is very stable and it is accurate till there are no changes. But of course, it is computationally intensive. And when you are doing it for a large database, it takes a lot of time. So it is not practical, right? Obviously, for modern deep learning applications with huge data sets. So that's the issue here. So then we have the stochastic gradient descent. So what happens in stochastic SGD? We just randomly select training examples per iteration. So what happens that this will, of course, when all of those data set is not used, it will be fast. So updates will be faster, but it can introduce noise also, because when you are randomly doing, so the whatever is selected may not be related with each other. But the advantage is that this can help escape the local minima. So I'll move on and tell you and show you what is meant by local minima. Local minima means that the picture which I showed you before, it only had one minima and there can be multiple also. But the problem is that the updates are not very stable. Okay, and they may cause something just called they may result in something called as oscillation, going back and forth. Okay, so therefore it requires careful tuning of the learning rate. All right. So I believe you understand. I'll show you the picture again. And then is the mini batch gradient descent. So it is the balance between the both, right? So small batches of data, say for example 32 to 512 samples standard, to compute the gradients, right? And then it combines the stability of each batch gradient with the efficiency of the stochastic gradient descent, which we just discussed. And of course, this is the most commonly being used. So now with this understanding, I believe it will be easy to make sense of this. So this is the batch gradient descent. So all of this taken together, okay, and this is the stochastic. It kind of oscillates, okay, and the mini batch is the combination. So you take a subset of for kind of for batch gradient descent and then do a stochastic within that subset. So this is the one. Okay, so if you're interested, here is some reading material, more than some material. Now things may look very rosy and very simple. Even with a single minima, there can be issues. Okay, so there are certain critical points, because remember the blind man approach. The person can feel but cannot see. Same is true for these functions. Because we are looking at a search space. Remember, it's a search space. It's not an image. It's a search space. For your sake of comprehension, I have showed you in the form of an image. So what are the different critical points in that search space where the gradients vanish? They don't exist. For example, if it's a straight line or a plateau, the gradient is zero, right? So and you really don't know how big that plateau is using the blind man approach. And of course, so what is the impact on the descent? So there are different critical points where the gradients vanish. Vanish means the gradient becomes zero. And of course, they will significantly influence the process of optimization, especially for the deep learning. And why? Because the landscape is highly non-convex. Convex means that you have say for example a picture or a diagram, and you join on the parameter of that figure, right? You connect 2 points, and the line and the connecting line resides within that picture. That is convex. But in real life, the landscape is highly non-convex, right? So you understand. I'll show you more again. So that is true for deep learning. Why? Because there are so many parameters, right? It cannot be convex. So there's something called as a local minima, then is the global minima. So local minima is the point, or okay, while descending that mountain, which is lower than the nearby value. But of course, that is not the actual valley where that blind man is going. And at the local minima, the gradient vanish. Okay, and it may stop because it has reached a minima, right? And but in deep learning, there can be many local minima. So this has to perform well so that it doesn't get stuck in the local minima. Okay. So but sometimes it is acceptable to reach the local minima sometimes. Then is the global minimum. Okay. It means that the loss function is the absolute lowest value. Again, the gradients are zero at this point. Okay. What does it signals is that the training is complete. This is something which is ideal, right? But it is expensive and it may not always feasible to find the global minimum, right? especially when the search space is complex and it's non-convex. All right, so let me take, show you. So this is the minimum, right? This is the maximum. And if we were to say the global minima or the local minima, so if we had something like this, okay, then this is the local minima, this is the global minima. Or if we had something like this, okay, so then this is the global maxima, and this is the local maxima. Okay, so what are saddle points? So first, saddle points are flat regions. Okay, saddle points are flat regions, right, where the gradient is zero, because you see this is kind of straight. I'm sorry, let me close this. Just a second, please. So what is a saddle point? Saddle point is a region where the gradient is zero. Okay, it is not the minimum. It is minimum in this direction, right? But it is maximum in other direction. So what can happen that the blind man may stop here because it doesn't know. It has to like move around a lot. So it can slow the training, moving around, and then finally find the place. And of course, in high dimensional models, this becomes an issue. Then is the plateau. So plateau is larger than the saddle point. It is called a saddle point because it looks like a saddle, and you see that this is the global minima and this is the local minima. Okay. So so the gradient descent struggles for a plateau because you see that the straight area is a lot. So the training can actually stall. It can stop, right? And so that creates a problem, and you require adaptive learning rates to escape from here. And similar to the minima is the maxima. So I hope you understand this, and with this we end lecture 3A.